Okay, let me start again on the chapter 4. On the chapter 4, we are going to study the mechanical property of the material. And this chapter is the same as the one we have studied from the mechanics of material. And if you may recall what we have the stress strain diagram. This diagram is from what's so-called the tension test. And from the tension test, we have the specimen, and that specimen is in the applied force. So the stress is from the P divided by the area, and the area is measured from the diameter, and it's going to be pi d square over 4, or it's going to be pi r square. And when you apply the force, the specimen will elongate, and by doing that, you can compute the strain by the elongation divided by its original length. By doing this, you will have the data, and then you plot the behavior of the material. That's called the stress strain diagram. And from the stress strain diagram, you can see the first part of it has a kind of linear, actually it's linear and elastic behavior, and most of this is linear. Only a small part of this is non-linear. And the other part of this behavior, as you may know, is going to be the plastic behavior. This second part going to be the plastic behavior. After you get the stress strain diagram, the learning objective requires you to find the property of the material. Why? Why we need to find the property of material? Because when you select the material in our construction, you will select material, and then you got to specify the property of the material, such as this one is the steel. Okay, the steel also follow the Thailand industrial standard, in which they require you to determine 4 important properties. First, they require you to find the yielding stress, and second, they require you to find the ultimate stress, and the third one, they require you to find what's so-called the E is the modulus of elasticity. And also the fourth, they require you to find the percent elongation. How can you determine it? The material property for this material, you know from the previous lecture, the yielding will be determined at this point. Okay, and the ultimate will be find by using the stress strain diagram, and the sigma ultimate supposed to be at this point. Okay, and then if you determine what's so-called the modulus of elasticity, modulus of elasticity is the slope in the linear elastic portion. That E is going to be the delta sigma over here divided by delta strain. And then for the percent elongation, that is the formula to find it. And what the percent elongation mean? Yeah, that means you're gonna check the ductility of the material. If the steel has high ductility, that means it will deform a lot before its failure. And if you go back to the subject, the percent elongation will determine from the final length minus original length divided by original length, and then times 100%. Most of the time, the steel will have percent elongation larger than 20%. Okay. What the meaning of the modulus of elasticity? This one shows the stiffness of the material. So if the material has the high modulus of elasticity, for example, E sub S, the modulus of elasticity of steel has the value of 200 gigapascal compared to the E of the concrete, in which usually it has the value between 20 to 30 gigapascal. That means the steel is stiffer. That means it has less deformation to a given load compared to the concrete. And what the yielding and the ultimate stress measure is going to measure the strength of the material. Higher yielding stress, that means the material has the higher strength. For example, the sigma sub y of the steel is 250 gigapascal. It is larger than the stress of the what's so called the concrete. Concrete have the strength of ultimate compressive strength. Usually for the typical concrete is going to be 20 to 40 gigapascal. That is for example. And then when you understand the stress diagram, you understand the way to determine the mechanical property. You also understand the meaning of this given mechanical property. And then you are going to apply the Hooke's law. The Hooke's law is the special portion. The Hooke's law will be applied in the linear elastic behavior, in which this region from this formula, the stress is proportional to the strain. And most of the analysis and the design in civil engineering will follow, most of them not will, but are following the Hooke's law. And we used to study this Hooke's law in the chapter 3 and the chapter 4 of the mechanics of material. Okay. And then after that, we're going to determine the deformation of the structure. For example, if we have the structure that's made by the steel, it has the stress diagram as above. Okay, under the application of the force, this specimen will have the stress inside it. If you like to determine the stress, you got to cut it, and then you draw the Fibonacci diagram of this portion of the structure, and then you can determine the internal force. And since this member is to force member, and you can see it is in tension. In this way, you can determine the force here. For example, this is AB. This is going to be F sub AB equal to the force applied here. For example, 10 kilonewton. That is going to be 10 kilonewton. And then by doing this, you can compute the stress. Sigma sub AB is going to be F sub AB divided by the area A sub AB. Okay, if the stress here is less than the yielding stress here, that means the specimen gonna have elastic behavior that's going to be in this region. And again, if you cut the specimen here and then you draw the Fibonacci diagram under the application of the force over here of, again, if this is 10 kilonewton, this is going to be 10 kilonewton also. And the force that occur here gonna be F sub, let's say BC. And then when you know F sub BC is equal to 10 kilonewton, so F sub BC will be used to determine stress of this member, F sub BC divided by A sub BC, sorry. And then you do the comparison. If this stress is larger than sigma sub y, the behavior of this portion gonna be in plastic region over here. So in a same member, the structure may behave differently due to the stress that occur due to the applied forces. And then when you determine the deformation, you have the equation of stress equal to deformation divided by length. And then if you write this one, the deformation will be strain times L. Since this behavior is elastic, the way to compute the strain will follow this equation. So this one, the strain of the AB in the elastic behavior will be the stress sigma sub AB divided by the E. However, when we come to the strain of this portion for sigma sub BC, the behavior is what? Is plastic. We cannot use the Hooke's law. By this way, you can determine the strain of what? The strain of this BC. This is BC. This is BC. From what? From the stress strain diagram. Okay, this is different. The plastic behavior you got to determine from the stress strain diagram. However, from the elastic behavior you can determine from the Hooke's law. And then the deformation of this one will determine from delta sub AB. From this equation will be equal to strain sub AB times the L sub AB. And finally, the strain for this one will be used to determine the deformation of BC equal to strain sub BC times the length BC. And then for the total, we'll just combine what we have of the state of deformation AB plus the deformation of the BC. This is for the third learning objective. And for the last one, oh, not yet, it's not finished yet. And then after release the force, we're going to determine the deformation for that again. But I will talking about that later. I just introduced to you about how to determine the deformation after the structural member subjected to the applied loading. Okay. And the last one we will discuss about the creep and fatigue. I will talking about that later. Okay, this is the introduction of the chapter 4, and I will talking about the detail of this later. Okay, come to the more detail of this. I told you from the previous slides about the stress and about the strain, and you may see that the stress and the strain come from what's so-called the external forces. For example, this one is external forces, this one external forces, and external forces actually supposed to be moment. In some cases also, it will produce what? It will produce internal forces and moment. For example, this is the resultant internal forces, and this is the resultant internal moment. The moment and the force, okay, is just the way we use to find the effects inside the structure. Usually, we consider this one at the centroid of the section. And in actuality, the structure is subjected to the stresses that distribute across the whole section of the structure. I mean, in reality, these internal forces and moment is determined from what's so called the Fibonacci diagram and the equation of equilibrium, and then is used to determine the stresses. For example, if your structure is in tension as before, if this structure is just be in tension and then you cut it, okay, the external force will produce the internal force, and then what we use in the mechanics of material, the stresses occur in this section will determine from this internal force that is going to be P over A. And actually the F sub R or even the moment M sub R, the resultant force and moment will produce the force one in the perpendicular to the section. If you consider the small section here, we will have the resultant force delta F, and this delta F can be projected into one perpendicular to the section, another one parallel to the section. The one that's parallel to the section, we call this as the shear force, and the one that's perpendicular to this one, we call this for the normal force. Some people also call this as the axial force, and as you may know, the axial force will further produce the what's so called the normal stress, and we call this as the sigma. And the shear force over here will produce what's so called the tau, which we call this one is the shear stress. Okay, so that means normal force produce normal stress, and shear force produce shear stress. And then we come to this. The normal stress, as you may know, is can be classified into tensile stress and compressive stress. And most of the time, the tensile stress cause the tension, and the compressive stress cause the compression. The tension cause the elongation, and the compression going to cause the contraction. Okay, they are in the opposite thing, and when you consider these two, the effect of tension and the effect of compression are different. Anyway, under the application of the compressive force for this one, and you can compute the effect of the external loading into these stresses that's uniformly distributed across this section, and the equation that you use will be the internal forces divided by the area. Okay, that's a simple equation. And then another one is the shear stress. Shear stress is due to the shear force. The shear force is parallel to the section of the member. That is different from this one. This is in the perpendicular to the section. This is in the parallel. And again, the shear stresses, the average shear stresses can be determined from the shear force divided by the area that I just show you here. And then there are a number of equations of this. For the axial force, we have sigma equal to P over A, and then the strength, as I show you, is elongation or contraction divided by the L. And then from this equation of Hooke's law, we have this one for P over A equal to A delta over L. For the linear elastic, we can compute the deformation of the structural member basis on this equation. But for the plastic, we cannot, okay? We must do the calculation as I showed you from the previous lecture. For the direct shear, the tau just equal to the shear force divided by the area, okay? And however, for the torsion, things are different. For the torsion, as the shaft of the car or the truck is subjected to the torsion has the arrow with double head. Unlike the force is just the arrow with one head. Okay, this torsion produces shear stress because when you twist this one as the reference line, when you twist this one, the red line, if you fix this one, the red line will be twist into the purple line. And then you will see this is going to be the angle twist, and this is going to be the shear strength. So in the lab, by people, you do the torsion. You can measure what? You can measure the angle twist. Okay, you can measure the torsion. When you measure the torsion, you can determine the shear stress. Okay, if you recall from the mechanics of material. And then since the behavior is in linear elastic, the Hooke's law for the shear stress also be applied, and then you can determine the angle of twist, and then you may compare this equation with the one that you measure to confirm between the theory and to confirm with the one you can measure from the lab, and you can see most of the time they are close to each other within the linear elastic behavior. And then for the bending produce what? If you bend your finger like this, and then this is your bend. When you bend it by the moment, you will see on the top is going to be in compression, on the bottom is going to be in tension. It's different from the stress occur due to the tension, as I draw the picture for you. This one will compute by the equation of sigma equal to moment times y divided by I. Okay, and then there is transverse shear. You may compute by this equation, and shear flow. That is all the equation you have from the mechanics of material. I like you to go back and review all of this equation because you still need it in more advanced courses such as in the steel design. Understand, as I mentioned before, that the strength, when you have, for example, like the Y here, and then the Y attached to the handle over here, when you pull this, the wire will change from the length at the BC. For example, for 2000 millimeter is changed to the new one. This one will be longer than as we had before. Let's say if you have this one for 2002 millimeter, that means the wire elongate 2 millimeter more. By doing this, the wire is in tension. That means the normal stress occur in the wire, and the strength produced by the stress, and the definition of this normal strength is going to be the elongation divided by the original length. By doing this, we have the equation this is going to be 2002 minus 2000 and then divided by 2000. That means you're going to get this one for 2 divided by 2000. That is going to be 0.001. And this is the length, for example, millimeter. divided by millimeter. So the unit of normal strain gonna be length divided by length. Unlike the unit of this normal stress is going to be Newton per square meter, or many times we use it for megapascal, which is going to be Newton per square millimeter, because the stress always large, the normal strain always small. So the unit is very important for this. And again, normal stress produces the normal strain. The shear stress also produces the shear strain. Since the shear is trying to twist the specimen, for this one is going to lift this portion into this. And we also have another portion of this is going to be this one that's going to move this one in this direction. And before the application of the force, the angle here is 90 degrees. However, the units of shear strain is in radian. So we define this one as pi over 2. So it is the change from the perpendicular angle, and then is minus by the internal angle. So that means the average shear strain is going to be the combination of the angle here and the angle here. Okay, and the very clear example is this torsional member. You can see usually the member here start by have the perpendicular angle, and that angle just change, and you can compute the shear strain of this in the laboratory that we have for the torsional test. And then we come to the stress strain diagram. As you may know, the stress strain diagram basically come from the tension test. And then we have in the lab number 3, we're going to do the tension test for the steel, and we're going to do the tension test for the cast iron. Why we do this? Because these two materials are different. The steel is a ductile material, so it's going to have a kind of stress strain diagram. And differently, the cast iron is the brittle material, so the stress diagram of these two materials are different. We do what? We will start by measure the diameter of the specimen, and then we compute the area, okay, by using the pi d sub o square over 4, or you may use pi r sub o square. And then the stress is going to be the force divided by the original length. And again, during the test, the specimen will elongate. Usually, we must measure the original length. And then during the application of the force, the strain can be computed by the elongation divided by the longitudinal length. Okay, we put the specimen into the testing machine, and we measure the load from the load dial, and also we measure the elongation of the specimen here. That means we can compute the stress and strain for each load step. Okay, that means first one we have the load from 0 to 11.1, and then the specimen will elongate to 0.0175 millimeter. Since we have this one as A sub O, we divide the P by the A sub O, we get the stress, okay? And also we have the L sub O, we divide this elongation with the original length, we get the strain, okay? So when we do for each reading of what? Of the strain and of the elongation, you will have the stress and the strain. You get 1 point on the graph. You do it, and then you will plot the graph do we plot the graph in the lab? You got to do it by your hand. And since the graph on the first portion is what is very close to the vertical direction, this first portion of the graph, so you got to scale it up, okay, to make it clearer. If we scale it up like this one, we scale it up for what? For 100 times. For 100 times. For this one, for 0.1, for the lower graph is going to be 0.001. When you divide 0.1 by 0.001, it's going to be 100 times different. So that means you scale it up for 100 times. Okay. And then the important property, such as what? Such as the yielding, you will determine from this graph. If you like to determine the modulus of elasticity, again, you will determine from this graph, okay? And for the above graph, it is important for you to determine the what's so called the ultimate stress, and also determine this one. This is going to be fracture stress. Okay, most of the time we'll measure sigma sub y by this graph. We determine modulus of elasticity by this graph. However, for the sigma sub u and sigma sub f, we use the graph, the above graph, which is contain the whole behavior of the structure. Okay, and then again, there is some important thing that you got to notice about looking for the mechanical property from this graph, from the learning objective 2. No, sorry, for the learning objective 1, you got to read the graph to determine the mechanical property. Some are very important: the yielding stress, the modulus of elasticity, the ultimate stress, because this property specified in the standard, in the TIS standard. And then this is the example. Sorry, this is in Thai, some of them, but most of them you can read it in English. This is going to be structural steel section from the TIS 116. Okay, and this is the year now is the new one. This is the old one. And then you can see the TIS specify what? For the FE24, the yielding is going to be 2,400 kilogram square centimeter. The ultimate stress is not less than 4,100, and the percent elongation not less than 23%, and the modulus of elasticity not less than. Let's see, we use not less than. If it's less than this, you got to reject it. Okay, it's going to be unacceptable. If even one of these value lower than the standard, you got to reject it. The manufacturer must send the one that pass the yielding, pass the ultimate, pass the percent elongation, pass the modulus of elasticity at the same time. Okay. Okay. Now this point, this slide coming to the point for you to understand the big picture of the stress strain diagram. We use the steel. Okay, is for this is for the typical stress strain diagram of the steel to understand the behavior of the material. The material has big behavior, big type of behavior. One is elastic. This is kind of a rubber. You pick up a rubber band, you pull it, and then you release the rubber band. It's going to be go back to the original length. That means it's elastic. And then another one is going to be the behavior of plastic. Some set is inelastic. Okay, this one you pick up the plastic bag and then you pull the plastic bag until it's passed to some point, and then you release the force. There is some permanent set. Permanent set is have the permanent deformation in the plastic behavior. Okay, this is different. There is no permanent set for the elastic behavior, there is permanent set for the plastic behavior. And then the plastic behavior will be separated into 3 more portions. We will discuss this later. Okay, for the elastic behavior, we have this one for the elastic region. In the elastic region, when we apply the force to the specimen, the response will be in the linear behavior. And then if you put this one, the ruler over here and draw the line here, the one that the line separate from the curve, that point is the last point. That's the stress strain diagram is linear or proportional to the stress. We call this point as the proportional limit. This is proportional limit. Is the last point. That's the stress proportional to the strain. And if you increase the load a little bit more, the graph going to get a little bit curved and reach the point of the elastic limit. This is the last point. That's the behavior behave in the elastic manner. Okay, the point of plastic limit and elastic limit usually very close to each other, but in reality, it's going to have a big curve up here. Okay, when it starts for the portion of this yielding region. In the yielding region, what occurs is the steel, when we manufacturing it, most of the time the steel heat up to some point, and then is maybe under the hot rolling manufacturing process, the steel have the shape of I section or the L section, and then when it get cooler, the grain of the steel will attach to each other and they are randomly connected. When the stress reach the point of the yielding stress, the stress will start to move the random grain to be much more in order. By moving that grain, the strain just increase without increase of the stress. Okay, this portion is special. We call it yielding. When it reaches the end of the yielding region, the grain are in order. So the material start to have the strength to take care of a larger stress. However, the rate of this is slope of this is going to be smaller and smaller, and it's reach the slope of zero at the point what so called is the ultimate point, or the stress here gonna be the ultimate stress. And since this one has the stress increases or have more strength due to the strain here, we call this one as the strain hardening. Okay, it's strain hardening. It has the rearrangement of the grain in order, and when it's reached some point, reach the strain in order, it have more strength. It can take more forces, and then it's reached the ultimate. And in the lab, you will have a chance to look at what's so called the necking up until the ultimate. Now you may see the section of the steel. Usually when the stress is low, the section will be equal. However, when the stress passing the ultimate, you will have this kind of necking occur in the specimen. So when the specimen has the small section, the ability to resist the force also reduce. So this time the stress strain diagram will go down. Since when we compute the stress in this region, we still compute by the force divided by the original length, which is larger than the real section. That means the computation maybe get a little bit incorrect. But since the engineer usually working in this portion of the stress strain diagram, so this behavior not that much important. But if you prefer during the test when it's occur necking, you can measure the real section. When you measure the real section, the graph will get in this curve. Okay, this is going to be the two stress strain curve. It's going to be a little bit larger. And anyway, since we consider only in this portion, we're going to make things more simple. So most of the time, civil engineer consider only the engineering stress strain diagram in which is follow the part here. Okay. And this one we call is the necking region. This is a typical behavior of the stress strain that's shown in the stress strain diagram of the steel. Okay, and there is a lot of things here. I like you guys to review it. I put the right handwriting over there to show you guys about what you supposed to know about this. In the examination, I may put this one, for example, let's say this is the A, this is the B, and this is the C, this is the D, and this is the E. And I asked you, what is the A? What is the A? The A is here. You may answer me, it's the proportional limit. Okay. Or I may ask you, what is the necking? You may answer me, that is going to be the C. That is for example, okay? And this is going to be the necking. The student in group 1, group 4, group 1 to group 4 have already do the tension test. They have a chance to take a look at this necking, okay? And then when you plot the graph, again, you got to be able to read the mechanical property from the graph. For example, this is proportional limit up to 40. This is the upper yielding. This is the lower yielding. And most of the time we use the lower yielding represent the yielding we have in the design. And since the yielding and the proportional limit stress, they are very close to each other. Okay, they are close to each other. And the definition of the yielding is clearer. Most of the time we will allow using the Hooke's law at the end of the yielding region. Okay, and most of the time again we use the yielding to represent the strength of the material. And most of the time when we compute the allowable stress of the material, we just divide the yielding stress by factor of safety. So this is very important. And then the ultimate stress, and then the fractional stress. And I should note to you guys that when you find the value of this, you should not read it by the naked eye. Don't use the naked eye. Okay, you got to do the proportion to get this value, because if you use the naked eye to read it, you may produce some error. And also one more important thing, I should note that at the point of proportional limit, which is close to the point of the lower yielding, the strain at this point is about 0.0012 to about 0.0014. This value of strain is small. So at the point of yielding, the deformation of the structure is small. That is going to be small deformation. And this small deformation is one of the assumptions we use to analyze and design of the structure. And you should note that at the value of stress equal to the yielding, the strain can be as large as here. Okay, it means it's going to be very long strain. If you measure this one, this is at the end of the strain region. That means it's going to produce the strain of point OT, which is about 20 times larger than this. So if we use the stress at the yielding, that means the deformation of the structure at this point going to be very large, okay, in order that the objective of structure may not be satisfied. So most of the time, that means the discussion of this, the design code will specify the yielding stress, okay, because beyond this stress, we will have what? Beyond this stress, the steel will deform significantly and the structure cannot function as desired. Okay, so that means we usually use the sigma supply as the strength of material by this lesson. Our lesson first is close to the sigma supply, and then it will follow the Hooke's law, and at the end of yielding is produce very large deformation. Very large deformation. The structure will have the problem with the large deformation, so we limited the stress to that point. So the other portion of this structure is for what? That's for the reserve strength of the material. Okay, it still have more reserve on this. So anyone who design the steel structure and the steel structure collapse, that means you're going to have big problem, because in reality, what we use for this equation, we use it in the region of this yellow. If you design the steel structure and steel structure fail, that means there are a lot of error occur in your structure. Okay, and the failure of the material, as I mentioned, the tension test, we do the tension test for the steel, and also we do it for the cast iron. What we found is the steel is a ductile material. Steel can deform a lot before its failure, but the brittle material, we have the cast iron, we have at the brittle material, it can deform very small its failure. However, for the steel, the failure of the steel in the form of necking. So what happened here? In the tension test of the steel, okay, the necking occur. When the necking occur, what inside it is the slip of the plane of the steel grain. The slip of the plane of the steel grain occur due to the shear stress. So what it means is the steel under the tensile stress, the steel fail by shear stress due to the necking, due to the slip of the plane of the steel, and the plane is going to be 45 degrees with the longitudinal axis. Okay, unlike the cast iron, the cast iron is the material that has more carbon percentage in the material. So when the carbon inside the material, there is the micro crack between the steel and the carbon. When you pull it up, the micro crack just open up When the micro crack open up, the area that's receive the force less, and then what we have is the the cast iron that's in the tensile stress will fail by the open of the micro crack. That's open of the micro crack is due to the tensile stress and is occur due to the separation of the plane of the steel gate due to the open of the micro crack. Okay, and there is 90%. The plane is 90 degree. The plane is 90 degree with the longitudinal axis. That is important. The steel and the cast iron, they fail differently. And since the steel is the ductile material and the cast iron is going to be the brittle material, what they are different? The steel can deform a lot. Typically, the ductile material can deform considerably before its failure. Since it's deformed a lot, so it can absorb large amount of energy also. Okay, so we can use the steel in the area that require the large amount of energy absorption. And the brittle material is have the small deformation before its failure. If you compare the graph, the steel will have the state diagram in the form like this. It's going to be something like this. However, the cast iron will have the behavior something like this. Okay, it have very small deformation before its failure compared to the steel. The cast iron is an example of brittle. Also, the concrete is the kind of brittle material. How do we measure the ductility? The Thai industrial standard, they specify the percent elongation to measure the ductility of the material. When you test the specimen before this, when you specimen before the start, you have the length of L sub O, and then when you test it until it's failed, you have the length of L sub F. You put the L sub F and then minus by the original length divided by original length, you get the percent elongation. Most of the time you will see the steel have percent elongation larger than 20%, except the steel is high strength steel. The percent elongation may be less than 20%. There is another factor that's used to measure the ductility, and we call it the percent reduction of area. Before the test, we have to measure the diameter, and for the diameter, we compute for the original area for the diameter. Okay, and when the structural fail, you also measure the D sub F, the diameter at the fracture, and then you can compute A sub F equal to pi D sub F square over 4. So we have A sub F and then minus A sub O divided by A sub O. This is going to be the negative value. Okay, most of the time the percent reduction of area of steel is larger than 50%. Okay, and you can have this one in the lab. Next, there is the material such as for the aluminum or high strength steel, such as the P stasis wire that we use this in the P stasis concrete. The structure, the material didn't have the yielding point. It has an unclear yielding point. So for this material, we got to use 0.2% offset. This offset. Okay, this will follow the TAS and follow the ASTM. By doing this, what is 0.2%? 0.2% is 0.2 divided by the 100. That is going to be the 0.002. So you mark this one 0.005, this one 0.003, and this one going to be 0.002. And then you drag the line parallel to the linear elastic length. And then when it cut at the point, you can project it to determine the yielding stress. This is another way that you guys require to be able to do so. And then come to the stress strain behavior of the brittle material. There is the gray cast iron for this stress strain diagram, and you can see the cast iron, they contain high percent of carbon, and then the cast iron has the micro crack. When it is in tension, the micro crack open and the structure can fail abruptly or immediately or brittly. Okay, and the strength under the tension of the cast iron is very low compared to the strength of this cast iron under the compression. Okay. However, what is the reason why in compression the cast iron has very high strength? It can be explained in this way. Under the compression, the micro crack close. When the micro crack close to each other, there is also has the boson effect that cause the buck out. That means the area of the cross section in this area is larger. So the cast iron material will have the ability to resist the higher force. Okay, and as you may know from the test, it's going to be higher than the tension, at least 4 or 5 times for the gray cast iron. And this one also happens for the concrete. The concrete is, when it's in tension, it can resist the force very low. However, when it's in compression, it has a lot of strength to resist the force. Because of what? Because concrete composed of cement paste, and then bound the sand and the crushed stone together. And when it hardened, there is micro crack between the cement paste and the aggregate, the sand and the stone and the crushed stone. And when you put it, the concrete will be separated very quickly. That's produce very low tensile strength. However, when you put the concrete in compression, the micro crack just crush each other, and that's why the concrete will have this high compression capability. Okay, you may read from this. Both concrete and the cast iron, when it's subjected to the tensile stress, the tensile stress will cause the micro crack. Okay, in this brittle material expand rapidly. When it expands rapidly, it will causing the rapid reduction of the material cross-sectional area, and it fail immediately or abruptly. In opposite effects, when this one in compression, the micro crack close, and there are some lateral expansion due to the Poisson effect that will increase the cross-sectional area. That's why the brittle material here has very high compressive load carrying capacity. Okay, and now come to this graph. Let us consider the structure that's in tension. I may ask you in the examination, which material has the highest or also has the lowest strength? Which material has the highest strength? Okay, if you compare to this, you may answer to be the low carbon steel has the highest strength. Okay, if you still down, you may find the strength of the aluminum. This is 0.001, this is 0.05, this is 0.02. By using 0.2% and you drag the line here, that is going to be sigma sub y for aluminum. However, the sigma sub y for the steel, okay, going to be at this point. That's why the low carbon steel has the highest strength. Which one has the lowest strength? The rubber gonna produce the lowest strength. And then which material going to have the highest stiffness? For the tension test, which one going to have the highest stiffness? If you check for the stiffness, you just check for the slope. You can see the steel has the highest stiffness. And again, you also see the rubber have the lower stiffness. Okay, which one can be considered as the brittle material? Okay, which one can be considered as the brittle material? You can see the cast iron, okay, can be considered as the brittle material, and the wood also. This one are the brittle material. Which material can be considered as the ductile material? That's maybe asking you like this. So ductile material can be aluminum alloy, can be low carbon steel, can be the rubber. That's for example. Or in the opposite, may I ask you the other thing, like basis on the graph, which material gonna have the also is a way have the highest Poisson ratio? Which one going to have the maximum Poisson ratio? You guys may answer to me that is going to be the rubber. That is going to be around 0.4. Which material going to have the minimum Poisson ratio? Okay, aluminum and carbon are very close to which one? Or if you prefer to this, if you consider the whole diagram, you may say the complete going to have the lowest Poisson ratio. That is about 0.1. Okay. There is a lot of questions that may ask you. I may also ask you about the definition. What is the definition of strength? Okay. What is the definition of stiffness? What is the definition of brittle material? Those kind of things. I would like you guys to go back and review about it. Okay. Okay. Let's go further to the Hooke's law. As I mentioned previously, Hooke's law only apply in the linear elastic behavior, and Hooke's law is important because Hooke's law is the basis for the analysis and design of civil engineering structure. Okay, that is important. And Hooke's law is special. You can see this is the soft steel have the strength about 200. This is structural steel have the strength about 280. This is machine steel has the strength about 450. The spring steel may have the strength about 1000. You can see most of these stress strain diagram of this material have the same slope. Okay, and within this region of the linear elastic behavior, we may write the equation of sigma equal to modulus of elasticity times state. And this modulus of elasticity is what? Is the factor that stays proportional to the strain. And it said, is based on this theory. This one can use at the point of proportional limit. And I did say to you, the proportional limit is very close to the yielding stress. And the definition of yielding stress is clearer than the proportional limit stress. So most of the time we allow to use this relationship up to the yielding stress by setting the proportional limit equal to the yielding stress. And by doing this, the E is the slope. Okay, since the E is going to be delta stress. This is going to be the stress divided by delta strain. And then it's going to be only in the linear elastic region, and it's going to be show, it will indicate the stiffness of the material, and for each material they are going to have equal modulus of elasticity. And strain hardening, when you stress the material in the elastic region, and then you release the force or release the stress, the behavior will be in the linear elastic region. Okay, anyway, if you pull the force to the plastic region like this, what happened is when you release the force, the behavior of structure won't go that way. The behavior of the structure will come in the way down like this, in which is going to parallel to the linear elastic part. This is called the strain hardening. And then there is so-called, this strain is the elastic recovery state. Okay, and this portion is going to be the permanent set. This permanent set defines the plastic behavior of the material. There is a good thing of this. By doing this, what we have is the yielding of the material. Usually, the yielding is only in this portion. Okay, after it changes, the behavior will come to this stress strain diagram. The yielding stress from the light blue into the blue. That means the yielding stress is higher. And since the yielding stress is higher, the modulus of Elasticity, which is the area of the stress strain diagram during the linear elastic portion, will get larger also. And the bad thing, usually before this, it can be formed a lot in the red area. After this strain handling behavior, it can be formed only this yellow. So it's reduce the ductility of this material, and it's also reduce the modulus of toughness, which is the area under stress strain diagram. Okay. Next, the strain energy. The strain energy is the strain stored in the material. You may pull the rubber band, and then when you release the force, the rubber band just go back, return to its original length. That means when you pull the rubber band store energy inside it. The energy during the deformation of the rubber band is called the strain energy. Okay. And when you pull the rubber band, we got this strain relationship, linear elastic. And you know that the area under this load deformation is going to be the work, and the work is the opposite of the energy. Okay, when we pull the rubber band, you do the work, and the work stored in the rubber band. That means the sign is just in the opposite. Okay, so when you consider this one as the energy stored in the material, the area here going to be 1/2 of this one is delta P, and this one is delta. So you have this equation from the area. And if you consider the small portion of this material element, you may see this one going to be delta X, and this one going to be delta Y. You have sigma equal to P over A. So delta P equal to sigma delta A. Delta A is going to be delta Y times delta X. And then the deformation of this is going to be strain equal to deformation times L. So the deformation equal to strain times L, delta Z. And when you put these two variables back into this equation, you rearrange it. That means you can determine the energy stored in the material equal to 1/2 of the state times the state in the linear elastic behavior, and also times the volume, because the volume comes from delta X times delta Y times delta Z. And then when we divide the energy by the volume, you got this one as strain energy density of U. And for the linear elastic behavior, you may use this equation to determine it. This one called the modulus of resilience. This is in the linear elastic behavior. And modulus of resilience is defined as the energy the material can absorb without the permanent deformation. It is important to design the structure to absorb the energy. For example, if the structure gets the vibration, this energy is important to absorb the vibration. And also, we have the modulus of toughness, which is the area of this material. Okay, and this is also the important material from this table. You may use this material property of the alloy, of the cast iron, of the concrete, of the steel, of the wood to compare with the one that you test in the lab. Okay, and then the last example, we coming to the tension test. Okay, they have some data and the stress strain diagram. They ask you to determine the modulus of elasticity between the proportional stress, modulus of resilience, yielding stress. I should specify this one. You will find the value from the graph with the detailed scale. Okay, and for the ultimate and the fracture, you will find it from the stress strain diagram with the large scale. Okay, and then you may put this one and then the graph. Okay, so for the AB, you may determine for this graph, which is going to base on this detailed scale. And for the C, you will use this graph to determine the mechanical property. Okay, so based on the first learning objective from the graph, you must be able to find the mechanical property. So the first one, modulus of elasticity. The modulus of elasticity must be found in the linear elastic portion of the stress strain diagram. So we expect the strain as 0.01, and it is still in the linear elastic. So we find the stress. So divide the stress by strain, you get the modulus of elasticity. And then for the proportional stress, you use your ruler and then you draw the line. Just draw the line. At the point that the line just separate from the curve, that is going to be the proportional stress. You may estimate this one to be about this point. This is 250. So you may say this is 255. Okay. And then for the sigma supply, you got to use the 0% offset because this material has no yielding stress. So you come to 0.002. By 0.002, that means you cut to at this point. Then you draw the line. You draw the line that's parallel to the first portion of linear elastic, cutting this point. And then you can see that is going to be about the point of sigma supply. After you do the proportion, you can determine the sigma supply of 335. Okay, 335. For the use of R is the area. Okay, when the material is in the linear elastic behavior. So you know sigma sub PL, and then for the sigma sub PL, you drop down here where it says up on the scale. Over here, you determine the proportional strength, which is going to be 0.0012. You put them together, you get this one into the 0.153 megajoule per cubic meter. And for the sigma sub U and sigma sub F, you can determine them easily. Okay, now later, you must use this knowledge. You must use this mechanical property and your knowledge of the stress strain to determine the elongation of the rod. And then this rod is what? This rod A, B, and C is the two force member. The ABC is in tension. Okay. And to determine the elongation of this, you got to first check the force inside it. This force applied here is 68 kilonewton by drawing the Fibonacci diagram. This is going to be F sub AB, and then summation of X sub X equal to 0. You will get F sub AB equal to 68 kilonewton. That is for the tension member. And also for this, if you prefer, you may cut this one and then you draw again the section. You must because it's going to show your understanding of the mechanic. This is 68 kilonewton, and then this is going to be the force F sub BC. Summation of X sub X equal to 0. F sub BC is 68 kilonewton. And then due to this, you can determine sigma sub AB will be what? Will be F sub AB divided by A sub AB. And also for this one, you have sigma sub BC equal to sigma sub BC divided by A sub BC. And then you got to check the behavior of this one. You will see later, this one going to be larger than, this one is big section. This one going to be smaller than sigma supply. This one going to be in the elastic behavior. However, what we have here is this one going to be larger than sigma supply. This one going to be the plastic behavior. So when you determine the elongation, one is elastic. You use what's so-called the Hooke's law. But for the plastic region, you cannot use the Hooke law. You got to find the strain plastic from the stress strain diagram. And then from the strain, you may find the elongation by this equation. You can determine this. And later, you release the force. When you release the force, the structure that is inelastic will recover to its original length of 500 millimeter. But the plastic will have some permanent set. They ask you what is the permanent set of the lot. Okay, so now the first one you find the elongation. Okay, and then you find the permanent set. We determine this by cutting the structure, and by the first one you got to draw the Fibonacci diagram and find internal forces of F sub AB and F sub BC, as I showed you before. And second, you find the sigma sub AB and sigma sub BC. Okay, for the sigma sub AB, just divide this by this is 20 millimeter pi r square. This is 216.5. For sigma sub BC is 387, and you can see this portion of this one is less than sigma sub phi, as I said. That means it's in linear elastic region. And then by the Hooke's law, sigma equal to E epsilon. And then you will have epsilon equal to sigma divided by E. So we have the E before, right? We have the 216.5. You determine the value of the strain. That is going to be very small. Usually it's very small. And then for the BC, we have the value of this is larger than sigma sub y. Is inelastic. Strain of this BC will find the strain diagram. Okay, so go back to this one, 384.8 something here. You project this one and find the strain here. So you read it from this file graph, file delicate scale. You have this one. So now you have the strain for the plastic and you have the strain for the elastic. Just use the strain equal to elongation times L. So elongation equal to strain times L. So you use this 500 is going to time this AB. And then for the 400, you time the strain of the BC. And then you get the total elongation. Now, the specimen, the structural member change for 900 millimeter to 904.8 millimeter. Now, we release the 68 kilonewton forces. Okay, by releasing this portion gonna recover to the 500 millimeter. Only this portion has the permanent set. Okay, based on this, only BC gonna have the permanent set. Okay, and then when it's recover, as in the strain hardening, it will recover in parallel to the first portion of this. That is going to be in parallel. And then what we have from the equation, sigma equal to E times strain. What we're looking for is strain here. Strain here is going to be strain recovery. So strain recovery going to be stress at the plastic divided by the E. You can compute this one. Okay, by this is going to be stress plastic divided by E, and then you get the recovery strain of 0.00175. And before that, you have the plastic strain of 0.0108. When you deduct the 0.10108 with 0.00175, you will get this one. This one is going to be the permanent set. Okay, so we have the permanent set of 0.00905 and only occur in the BC. So you time the length of BC. Now the permanent set is 3.6 millimeter. So what we have here is the member with 900 millimeter, and then under the force is 904.8 millimeter, and then after release the force, what we have is this one is going to be 903.6 millimeter. So this is going to be the final length of the structural member. Okay, that's finished the part of the lecture of this. But I still have to go to the lab. This one. Okay, let me show this one. On the lab, now we have finished some overlap. Okay, in this one. Okay, this one. Okay, we finish our lab for the week 1, week 2, and week 3. We finish this one, we finish this one, we finish this one. The lab number 3, now every one of you must have finished the lab report already, right? You should finish lab report for what we have for groups like this, and then you got to return this lab report to the Google Classroom. You're going to have lab on the Thursday, so that is the due date for you to send it to the Google Classroom. What you're supposed to be is you must have your lab ready and keep it at you, and you take the picture of the first page. Okay, you take the picture of the lab result past calculation. Also, you have the discussion. You take the picture of the discussion portion and the conclusion. Then you merge all the picture and you convert this picture into the PDF file, and then you set the name of the PDF file in accordance to those I post in the Line group, okay, and turn into the Google Classroom next Thursday. Okay, now we come to our portion. We're going to start to have the online lab for this session due to the COVID, and I don't think it's going to finish soon. So the group of 1, 2 going to be in lab 10, 11, and then group 3, 4 gonna be in the lab 9. Okay, lab 9 is going to be the fractional test, and 10 and 11 going to be the shear test, and PTA will brief you the lab. For the lab 10, 11, I will brief you after finish discussion on the lab table. And then next week, we will go further to the lab 5. That means you're going to go to lab 12. I will brief you next week. And also you will have the lab number 8. Everything required for the lab, the data, the video clip for the testing, PTA will provide you in the Google Classroom, and you will produce your lab report, okay, corresponding lab report, and turn in a week after the lab. Okay, that if you have further question, you may ask P. Kanjana, P. Poom, P. Oriya. Also, the senior of you have this kind of situation before, and if it's possible, you may ask them for help, or you may ask them for assistance whatsoever. Okay, and then I will go further to the lab number 10 and lab number 11. Okay, just let me put this one. Share again to another one. The lab. Okay. Let me brief you the lab a little bit. It may take about 10 minutes, okay, before we finish the class. We have the group 1 and group 2. We have the lab 10 and lab 11. Is going to be the direct shear. The first one is the direct shear for the matrix material, include brass, copper, aluminum, and that is going to be in the form of double shear. You know double shear, right? And next one, we have the wood. However, the wood, we're going to test it in the single shear and is in the parallel of grain. I first start by talking about the wood, okay? The wood, when we go up the wood will go up, and then the wood will have the grain of the wood parallel to the height of the wood. If you cut the wood and then you do the cross section of it, okay, and you will see the annealing of the wood. That's annealing count the age of the tree, okay, and the wood mostly will cut in the region of this annealing and use it and call it in the technical term as the timber. So we have the course called steel and timber design. We didn't have the steel and wood design because timber is the engineering wood. Maybe we just call it timber is equal to the engineering wood. Okay, what's so called the engineering wood is we cut the wood and sell the wood in the form like this. When you cut this one, so most of the timber will come in the piece, something like this. And you have what? You have the grain that parallel to the length of the structural member. Okay, so when you use the wood, most of the time we will use the wood, the timber in the parallel to grain to resist the force. And I will have this discussion to this later because this parallel to grain is practically uses in our engineering application. So now we will test them for what? We will test them to determine the shear strength. So that means you're going to shear the metal by double shear test. We will shear the wood by the single shear. The test will be very simple. And we also will take a note on the mode of failure of the metal and the wood in our study. Okay? And what we have now is the basis knowledge of this. When we shear this metal, what we have by the test of this, we will have this specimen fail by these two portions. When you cut this portion and draw the shear diagram, you can see the shear force of this gonna be F divided by 2. And this shear force is the direct shear. So this form will produce the direct shear stress across the section. And we can determine the average shear stress by the shear force divided by the area that shear force act upon. Okay, that is the area there. And the direct shear has 3 types. One is single shear, the second is double shear, and the third is pure shear. In the lab, we will use these 2 kinds of shear in our study. And for the single shear, you may see we can connect the structure like this one by using the bow. And by using this bow, you can see if you separate this piece of steel by the force of F, you may see we have the hole that's our bow gonna be put into this. If the pace will be in equilibrium, we require the force here. The force here is the F will be over here. The force also on the bottom portion is going to be, let me put it in this color, in this direction. So this force by the third law of Newton will apply here. So the force that acts upon the bow will cut the bow one plane. So we call this as the single shear. And then we will have the cut show over here. See, this is the evidence that we have due to the failure of the single shear that may be occur in the bow. Okay, and this one is a single shear. So since V equal to F, see the shear force here equal to F. So the equation is the force divided by the A. And you may see this one in this clamp. And for the double shear, many times we use the double shear in engineering. Okay, again, you may draw the Fibonacci diagram of the plate. By doing this, we have what? We have the plate. If this one is F, the resistance force over here is going to be half of F. And again, we have what? We have the hole that's put into this. So to connect them together, we have the bow. And then to make the plate in balance, the force F over 2 will have the force F over 2 here. And it's going to act here. And then also we have the force F over 2 here, in which is going to act F over 2 here. And then the force F here require the resistance force F here. And the resistance F here is going to be in this size of the bow, is going to be the F. So it's balanced. This is F over 2 plus F over 2 is going to be F. But this time the plane, the shear plane gonna be double like this. By using this one, the shear gonna be F over 2. Which one is to be this one, and then divided by A. Now the bow over here, is going to be the example of the bow that is in double shear. However, the bow over here, let's show here, this here is going to be in single shear. Okay, so the bow can be double shear and single shear. And at the same time, if you consider the timber, you may see by using this one, the failure plane of this timber are two failure plane here. So this time the timber is in double shear. So the wood or the metal, the wood and the metal can be both in the single shear or double shear, depending on the way we use this in our structure. Okay, come to the test. Let me start by the double shear of the metal. So the first step, Ajahn will have the metal specimen. Is maybe the brass, the copper, or maybe the aluminum. You use the vernier, measure the diameter of this one. So first one, you measure to the diameter D, and then you find the D average. From the D average, you can find the average area of this one. And then the second one, I like you to weight specimen. And when you weight specimen, you also need to measure the length. Okay, you just compute the density of each specimen. It must be aluminum, brass, and copper, and you just divide the weight of aluminum by the volume of aluminum. I like you guys to determine this. This second step is the new one. We didn't do it for the previous one. And then the third step, okay, you need to come to this. You need to adjust the handle until the hole over here is clear. Okay, you just install the specimen. You just put this one into this. Okay, and then the force, you perform the test. This time you put the needle. You move this needle, the black and the red come together. Okay, and then you increase the load by rotate the handle slowly. And then what you can see is the needle will be increase. And then when it's reached the limit, okay, the black needle will separate from the red needle. And then you read the P maximum. And then the fifth, you take note on the failure of the specimen. Okay, you got to draw the picture of the specimen, and you can see the metal specimen. Part of this is going to be very clear. A portion of this very clear, and part of this you will see some texture. Okay, you must draw this one. It's going to be the same for this three metal, and we make discussion. And you're supposed to be understand that for the clearing portion, this is the way that's the metal cut by the testing fixture. Okay, but for this portion is the portion that the material failed immediately. You will hear the sound click during its fail. Okay, and then for the wood, you will have the specimen in the form like this. You must measure all the dimension of the specimen, and then after you measure the specimen, then the second you weight it. And then you find the low of this by putting the weight divided by the volume. Most of the time, the specimen has higher density. They're supposed to have the higher strength because the higher density wood has more grain and can take more loading. Okay, and then the third, you just install your specimen into this casing. Okay, and then you put all of them into the compression machine, and the specimen in this way is going to lock. Okay, by the steel casing is going to lock in this way. And then when you apply the force will transfer by the steel plate here, and then you just turn on the machine and increase the loading. So before increase the loading, just put up the peak recorder when it's increased the force and then to the max. Okay, the failure may occur usually since this grain is in this direction. Most of the time, the crack will occur like this. Okay, and then the force step, you just notice the failure. Okay, and then you determine the area of the crack. And then you can find the tau equal to P max divided by the area. That is going to be very easy to determine. And what happened is sometimes the crack is not like this. Sometimes it's cracked like this. If it's cracked like this, for example, is this one cracked like this, and the other one cracked in this way, we're going to measure the crack. Okay, you measure the crack. You measure the one in the light blue and do the average. Okay, let's see. This one going to be A1. This one going to be A2. So we have the A average equal to A1 plus A2 divided by 2. Again, you also have the B1 and this one is the B2. And you have the B average equal to B1 plus B2 divided by 2. And then the area that I just mentioned previously here will be compute equal to A average is going to be AVG, and then it's going to have B AVG. Okay, let's see, we have this, and then we will have the area divided by the maximum force, and then you can determine the ultimate of this. Okay, for double shear also, you can have this one and then just divide the maximum force. This one will be tau equal to P max divided by 2 because this is double shear, and then divided by the A average. Okay, and then you may put this one just sketch. So you must sketch this one. You cannot take the picture. You must sketch the test setup, and you may record the testing result, and then you got to sketch the failure mode, and you do the discussion and conclusion. You take the picture, you make it as the PDF file, you set the name and turn it into the Google Classroom. Okay, that is for the metal. The next year for the steel, sorry, it's not steel, it's brass and copper and aluminum. And this one for the wood, do the same thing. Okay, thank you very much. That is the end of this lecture. And we will have the online laboratory on Thursday. Hope you guys have a nice day and also be safe from the COVID. Okay, bye-bye. Thank you very much. Okay, after that we already finished it. Okay, anyway, thank you very much. And if you have further question, may ask me and may ask PTA in the live group. I will answer you as soon as possible. Bye-bye.